In the first module, covering natural gas liquids measurement, you were introduced to NGLs and NGL measurement. You also learned about some of the problems that can affect NGL measurement accuracy. Now, in this second module, dealing with NGL measurement, we'll take a closer look at NGL metering devices. We'll also look at some of the basic principles and steps involved in proving or witnessing a NGL meter.
This is the first section of a two-section module dealing with natural gas liquids measurement.
As mentioned in Module 1 of NGL measurement, natural gas liquids are an important part of our revenues. Measurement of these liquids is very important. Now, in this section, we'll look at some of the meters used to measure NGL volume. These meters are classified as volumetric or inferential. And we'll also look at some of the methods for measuring the density of NGLs. To measure the volume of NGLs, orifice, turbine, or positive displacement meters are commonly used. So let's take a moment now to talk about each in a little more detail. Starting with orifice meters, like this one.
The orifice meter is one of the oldest types of inferential meters. The term inferential refers to the fact that the volume is determined from some activity associated with NGL flow. For instance, to determine the volume of NGLs with an orifice meter, the temperature, orifice meter, differential pressure, and static pressure, or static constant, must be known. The orifice meter station creates a differential pressure and records the differential pressure and sometimes the static pressure. For a more detailed discussion on orifice meter stations, review the tape on orifice meter station fundamentals.
Another inferential meter is the liquid turbine meter. Now, the liquid turbine meter is an inferential device which measures flow rate in the meter tube. It functions by sensing velocity of fluid passing through a known cross-section of the meter tube.
As the fluid passes through the meter housing, it causes the rotor to spin. The speed of the rotor is directly proportional to the velocity of the fluid. Because this velocity is determined by the volume of fluid, rotor speed can be used to calculate volume flow. Turbine meter construction is relatively simple. The meter itself is installed directly in the meter tube. The meter is a precisely balanced, free-running rotor mounted in a cylindrical housing, similar to a flanged pipe. This unit is mounted on the pipe center line. A magnetic pickup assembly is positioned as close to the rotor as possible but does not penetrate the housing. As liquid passes through the meter, it causes the rotor to rotate. The rotor blades pass through the magnetic field of the pickup and generate a pulse in the pickup coil assembly. Each pulse represents a distinct unit of volume. Added over time, the total pulses represent the total volume metered. The turbine rotor is mounted on a shaft by an up and downstream hanger assembly. Although these hangers might resemble straightening vanes, they do not perform this function. The turbine rotor blades are set at a predetermined angle. This angle relates the flowing stream, angular velocity of the rotor, and the frequency of the meter. The rotor rotates on the center line shaft by means of a bearing. This bearing is either lubricated by the meter fluid itself or permanently sealed. However, to minimize the load on the bearing, the rotor also floats. Now, this floating occurs as liquid entering the meter is deflected outward by an upstream cone, which increases its velocity and causes a slight pressure drop. After passing the turbine blades, the flow is redistributed. Because the rotor hub is larger than the upstream cone, some of the fluid flows directly over the hub. The rotor then floats in balance between the upstream cone and the downstream cone. The magnetic pickup assembly is mounted on the exterior of the meter housing and counts the rotor blades as they pass. The blade tips of the rotor are made from or contain magnetic material. This material creates pulses in the pickup coil as the blades pass. These counts, or pulses, represent a unit of volume.
So far we've talked about inferential meters. Let's look now at a volumetric measurement device, the positive displacement meter.
This meter continuously divides the flowing stream into known volume segments. The segments are isolated momentarily, counted, and then returned to the stream.
There are numerous types of positive displacement meters. They include the piston, rotating disc, rotary sliding vane, oscillating piston, rotary bucket, screw and spinal vane.
Commonly used meters are the rotating sliding vane and the oval gear. The positive displacement meter consists of an external housing, an internal measuring unit, and a counter-drive train. Let's look at each of these in more detail. The external housing is a pressure vessel with an inlet and outlet for connecting the meter to the tube. Depending on their pressure rating, these meters may be of single or double case construction. In single case construction, the external housing serves as a pressure vessel and as the outer wall of the measuring unit. With double case construction, the external housing serves only as a pressure vessel. Inside the housing is the precision measuring unit, made up of the measuring chamber and the displacement mechanism. The counter-drive train transmits the internal motion of the measuring unit into a usable output signal. This train may be a mechanical gear train, a magnetic drive coupling, a contact closure, differential inductance pickoff, or a combination of the above.
Now that we've seen the basic components of the positive displacement meter, let's look at two meters, the rotary sliding vane and the oval gear.
The rotary sliding vane meter consists of a single or double case housing, a cylindrical rotor which revolves on a ball bearing around a central shaft, and a stationary cam. The rotor has 4 or 6 evenly spaced slots which provide guides for the blades. As liquid flows through the inlet against the extended blade, the rotor and blades revolve. This rotation around the fixed cam causes the blades to move in and out as the blade rollers follow the contour of the cam. The blade nearest the inlet moves outwardly toward the chamber wall and is fully extended at the beginning of the measuring chamber. As the preceding blade is also extended, a precise measuring volume is formed between the two blades, the rotor wall, chamber wall, and top and bottom covers. For each rotor revolution, 4 or 6 of these measured volumes are produced. A small pressure drop causes the rotor and blades to rotate, while a liquid seal between the blades and the chamber wall assures separation of the measured volume. This type of meter maintains a continuous flow of uniform velocity. The oval gear displacement meter also divides the fluid into measurable volumes. As liquid enters the inlet, one oval gear begins to isolate a volume, while the other releases its volume. As the gears rotate, one rotating clockwise and the other counterclockwise, a precise volume is measured. The density of an NGL stream is determined by use of a gravitometer, or more typically, a densitometer. The densitometer measures weight per unit of volume as compared to water weighed in a vacuum. If a gravitometer is used, it records the specific gravity of the liquid stream, and then the reading is converted to density by multiplying by the weight mass of water per unit of volume in a vacuum at 60 degrees Fahrenheit. There are basically 3 types of densitometers: the insertion or inline types, slipstream or strip sampler type, and the non-intrusive type. Densitometers can also be characterized by measurement method. All insertion densitometers are the vibrating type, while slipstream densitometers can be either balance beam, buoyancy, or the vibrating type. The vibrating densitometer utilizes the vibration momentum principle. A sample of the liquid stream flows into the densitometer. The densitometer is vibrating at one of its natural frequencies, which is proportional to its mass per unit length. Because this vibration is also proportional to the density of the liquid in the densitometer, the density of the liquid can be calculated from the vibration frequency. The slipstream densitometer requires a pressure drop for liquid to flow through it. Commonly, an orifice plate is specially installed to create the pressure drop for the densitometer. Another device used to create flow through the densitometer is a pump in the slipstream. Densitometers can be installed at several points on the meter run. However, the primary concern is that density is measured at flowing conditions, the same as those of the volume measurement. An insertion type densitometer can be located either up or downstream of the metering device. However, because its insertion creates turbulence, the densitometer should be placed some distance from the meter. All piping for slipstream densitometers should be insulated to keep the temperature the same as that of the flowing stream. The accuracy of densitometers is dependent on several factors. These factors include that the insertion type obtains liquid that is from the middle third of the meter tube, that the slipstream type has large enough piping to allow sufficient flow through the densitometer. The product is in single-phase condition, and any solid matter in the liquid is minimized. This concludes this first section covering NGL measurement meters. Take a moment now to review the material in your student manual. Preview this tape again if needed, and answer the questions at the end of the section. In our next section, we'll cover meter proving.
In our last section, we look at the different meters that are used to measure NGLs. Now in this section, we'll see how some of these meters are proved and witnessed.
This is the second section of a two-section module dealing with NGL measurement.
Maintaining accurate measurement of NGLs requires periodic testing of the measurement devices. If inaccuracies are found, immediate steps must be taken to correct the devices. For orifice meters, the testing involves our checking the primary and secondary elements. At other times, a representative of ours may witness someone doing the checking. With turbine meters, positive displacement meters, and densitometers, the test means proving meter accuracy with another calibrated instrument. Again, depending on contract conditions,
We may do the proving.
or an ARCO representative may witness the proving.
The purpose of witnessing in the measurement of NGLs is to ensure accuracy and validity of the physical tests on the measurement equipment. Let's look at some of the points you need to know to be an effective observer at an orifice meter witnessing.
To be a good witness requires that you make preparations before the test, have the correct tools and equipment for the witnessing, witness the test, and are responsible for the actions and follow-up after the tests. Let's break each of these points down. Preparing for a meter witnessing requires planning. You need to schedule the tests in cooperation with all parties, make sure that all the tests can be done, that any associates needed for adjustment are available, and that any other services can be done at the same time. Be familiar with the current edition of ANSI, API, and GPA standards for NGLs. Be sure to have a copy of the contract brief for the facility. Take some time to review the history of the operation by comparing production reports with actual sales volumes for this location. Also review the reports for plate size, chart readings, and volume calculations.
Although you may only be a witness to another party's test, you should always be equipped to duplicate all the tests. You have the duty as a witness to see to it that test instruments are measuring correctly and proper test procedures are followed.
The minimum equipment you need for this includes dead weight tester, pneumatic gauge or water column differential tester, pycnometer, mercury check thermometer or an equivalent, meter tube and orifice plate micrometer. Bring extra correct size, well-maintained plates, steel chart scales, DOT approved liquid sample cylinders, transportation papers, and cylinder shipping containers, special meter tools, road maps, and directions to location. Witnessing begins when all parties have arrived at the test site. At that time, always create a good working relationship with the other party. Check the area for hazardous conditions, for example, corrosion, leaks, snakes, wasps, etc. Check to see that the meter station has been operating correctly. Now take the density readings and samples before taking the flow recorder out of service. Always remember to take the meter out of service and be sure to inform the proper personnel. Check for piping leaks. Check the differential element for calibration at a minimum of 5 points, both up and down the scale. See that the inking pens have the proper pressure against the chart, that the pens are in good condition, and the ink flows properly. Check the temperature recorder. Using the dead weight tester, check the static element for 0 according to contract requirements. Also check the differential element for accuracy and arc. Making sure that the orifice meter has been isolated and depressurized, then pull and inspect the orifice plate. With a senior orifice fitting, the isolation would not be necessary, but instructions for pulling the orifice plate should carefully be followed. After replacing the orifice plate, put the meter station back in service. Check for leaks and note the flow rate and recorder operation. Finally, complete the paperwork for all service performed. Remember, witness all activities and document all findings. Then sign the report. Never sign a blank form for tests not witnessed.
Sometimes in the process of a witnessing, errors or violations of a good measurement may occur. Discuss these observations with the other party, but always note the details on your report. If no agreement can be reached at the site, do not argue the point, but document the differences. The supervisors should then be notified to settle the dispute.
Liquid meter proving is the physical testing of the performance of a meter that is in service, measuring the flow or volume of a stream. The meter proof is performed by placing a meter in series with a meter prover, which has a known base volume for standard conditions. The prover is installed so that during a test run, all product measured by the prover is also measured by the meter. Alternately, only the product measured by the meter is measured by the prover. At the end of each known volume passage, the meter measured volume is compared to the prover volume. Field provings of turbine and positive displacement meters use either unidirectional or bidirectional pipe provers, a master meter, or possibly a portable small volume prover.
In a unidirectional prover, a trip or known volume is defined by the displacer traveling from detector 1 to detector 2. For a bidirectional prover, a round trip is the displacer traveling from detector 1 to detector 2 plus traveling from detector 2 to detector 1. The displacer in a pipe prover is typically a sphere. However, a piston may also be used. As the displacer moves between the detectors, a fixed volume of NGLs is measured. During the displacer trip, a pulse counter records the number of pulses generated by the meter. To prove a meter using a bidirectional pipe prover, you need to first record the operating flow rate, temperature, and pressure at the meter. Direct the flow of the meter being proved into the prover. Check all valves to see that none of the flow through the meter is bypassing the prover, and none of the flow through the prover is bypassing the meter. Adjust the flow of the meter to its delivery flow. It may be necessary to make several trial runs to bring the prover and meter into stable temperature conditions and purge the system of gas and air. Now, check the prover totalizer or counter against the meter totalizer. Then zero the prover totalizer. Once the prover and meter are stabilized, launch the displacer by activating the four-way valve. When the displacer has passed detector 2, record the pulses and adjust the valve to reverse the flow. When the displacer passes detector 1, the counter displays the pulses for the round trip. Record this reading and zero the counter for the next trip. To establish repeatability, 5 out of 6 consecutive round trips are made that give volumes within 0.05% of each other. Master meters are desirable where space or remoteness prohibit the use of standard pipe provers. To prove a meter using a master meter, you need to make sure there is a working strainer upstream of the master meter, and then connect the master meter. Record the operating flow rate, temperature, and pressure of the flow meter. Now direct the flow of the meter being proved into the master meter. As in proving with a bidirectional pipe prover, check all valves to be sure none of the flow through the meter is bypassing the master meter, or that the flow through the master meter is bypassing the meter being proved. Adjust the flow rate of the meter being proved to its delivery flow. Run several trial runs to bring the master meter and meter into stable temperature conditions. Now check the master meter totalizer against the meter totalizer in terms of pulses per unit volume. Once checked, zero the master meter and attach totalizers. Gate the two totalizers together and measure the volume with a minimum of 10,000 pulses. Stop the two totalizers simultaneously, record the readings, and zero the counters for the next measure. Again, to establish repeatability, 5 out of 6 consecutive proves within 0.05% of each other are required.
The purpose of proving a meter is to produce a correction factor for the meter. This correction factor, usually noted as C prime, is used as a multiplier to the totalizer difference in order to produce volume corrected to base conditions.
4 principal correction factors are used in proving meter volume. They are CTS, the correction factor for the effect of temperature on steel; CPS, the correction factor for the effect of pressure on steel; CPL, the correction factor for the effect of pressure on liquid; and CTL, the correction factor for the effect of temperature on liquid. Further, steps for meter calibration and adjustment are in your manual. Just as volume measuring meters must be proved and calibrated, the densitometer also must be proved. To prove densitometer accuracy, a pycnometer is used. A pycnometer is a high-pressure vessel of certified volume and empty weight. NGLs flow into the pycnometer A volume is captured and then weighed. Density is found by dividing the net weight of the NGLs by the known volume of the pycnometer. The physical proving of the densitometer includes verifying the pycnometer empty weight, purging the connecting lines for the pycnometer, connecting the pycnometer to the flow line, pressurizing the lines and pycnometer to stabilize temperature and pressure in all vessels, insulating the lines and pycnometer, filling the pycnometer, isolating the volume by first closing the downstream valve of the pycnometer and closing the upstream valve, disconnecting and weighing the pycnometer as quickly as possible, establishing repeatability by repeating the steps until two samples give weights within 0.05% of each other. Steps for calibrating the densitometer are in your manual.
This concludes our second module on natural gas liquids. Take a moment now to review your manual. View this tape again if necessary and answer the questions at the end of this section. Now, in this module, you've seen the various devices and methods for measuring NGLs. You've also seen the various pieces of equipment and steps necessary to maintain the accuracy of these devices. Remember, natural gas liquids, like natural gas, are an important part of our oil and gas companies' revenues, and an accurate measurement of these liquids depends on the proper use and maintenance of these devices used to measure them. And that, of course, depends on you.